All right, hello and welcome to 4.4 video. So again, as a quick reminder, you may want to print out the PowerPoints and take notes. Feel free to pause the video, rewind, or rewatch examples as necessary. So in 4.4, we're going to look at quadratic functions a little bit deeper. In this case, we're going to look at the word problems. All right, so typical buzzwords here, we're going to call these models, right? We're going to look at applications of quadratic functions, right? and how they might apply in the real world. All right, so the first example says, the marketing department at Texas Instrument has found that when certain calculators are sold at a price of P dollars per calculator, the revenue R in dollars as a function of the price P is given by this model. So they give us R of P equals a negative 150 P squared plus 21,000 P. So again, notice that the way this function is being given to us, price is the independent variable and revenue is dependent. So depending on the price we charge, that will determine our revenue, right? Which makes sense, right? The less we charge per calculator, probably the more calculators we're going to sell and the more revenue we're going to make. In theory, right? Probably the more we charge per calculator, probably the fewer calculators we'll sell and the less revenue we'll make. So revenue is definitely a function of the price. So the question here says, what unit price should be established to maximize the revenue? And if this price is charged, what is the maximum revenue? All right, so again, if we think about the fact that we're graphing a quadratic function, right? This quadratic function has a vertex. And since this leading term is negative, the parabola will open down, and therefore the vertex will be a maximum. So we need to find the vertex of this quadratic. Right, so here's our quadratic function, and here is the graph of that quadratic function. Right? So if we were to locate that vertex with negative b over 2a, we would find out that the x value of the vertex is 70. Right, so if we take, here's my b value of 21,000, here's my a value of negative 150, and if I do b over 2a, I'm going to get the $70. And again, I called that the x coordinate, but remember in this case, my x values are my prices. So in this case, my x value is the price of $70 per calculator. So notice down here I'm saying that the TI, Texas Instrument, should charge $70 per calculator to maximize their revenue. Now, if I were to take that $70 and plug it back into the revenue equation, I'm going to get this y value, $735,000. So that, remember that in this equation, right, the y values of the vertex are the revenues. So if I were to charge $70,000 per calculator, then my maximum revenue I would achieve is the $735,000. And again, I didn't really show you any work here because I wanted to focus a little bit more on the concept. But not a whole lot of work to show, right? In reality, I would just do negative b over 2 times the a value, and that would give me the value of 70. I would plug that into the equation and get the y value in return. Okay, so this is the basic concept of this whole section. Now I picked a pretty simple example to begin with where they gave me the equation of the parabola, and then all I had to do is find the vertex. They all won't be this easy, right? Sometimes we're going to have to build the quadratic model. So if you think back to section 3.6, where we practiced building models, we're going to see some of those problems in this section. Let's take a look at an example. So in this example, it says that a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So we want to maximize the area. Now, in this problem, what you're going to notice is they didn't give me any equation. So in the prior example, they gave me the quadratic revenue. In this example, we don't have any equation. So we got to build the equation. Now think about what it is we're being asked to do. We're being asked to maximize the area, right? What dimensions of the rectangle enclose the most area? So I need to build an area equation, and I'm going to maximize that area. So what we're going to find out pretty quickly is the area is a quadratic. It's a parabola. It's going to have a maximum. So let's think about what area is in general. Right? In general, area of a rectangle is length times width. Right? So in general, you know, the area of this rectangle would be x times w. That's my area. Now, the problem with this is that I have two variables over here. I don't want area to be a function of two variables. I want it to be a function of one variable. I want the right-hand side of this equation to be one variable. So I got to figure out a way to eliminate one of those variables and write it in terms of the other. So I look back up at the verbiage of the problem, right? It says that a farmer has 2,000 yards of fence. So that tells me about the perimeter. Right? So this is how I'm going to connect these two quantities together, x and w. So I know perimeter, you know, x plus x, right? Two x's plus two w's. That's my perimeter, and that's going to be all 2,000 yards of fencing. If I use that idea of perimeter being 2,000 yards, and the two x's plus the two w's is 2,000. Now I have an option. I could solve for w and substitute in to my area equation, or I could solve for x and substitute into my area equation. And I chose to solve for x. So I divided everything by 2, and then I decided to solve for w, apologize. And so there's my w equals 1,000 minus x. So what I'm going to do then is I'm going to substitute the w equals 1,000 minus x into my equation. So my area now is one variable. My area is a function of this length dimension x. So that was what we practiced back in 3.6, and in fact we had a really similar problem to this in 3.6, you may recall. And if you don't, no big deal, right? But so when I'm given the parabola equation, I just find the vertex, right? But the harder problems in this section are going to be where I don't have the parabola equation given to me. So in this case, we were maximizing area, so we had to build the area function. When we started off with our general knowledge of length times width, we quickly noticed we can't have multiple variables over here. So we went back into the problem, we looked for the given information of perimeter that allowed us to relate x and w together with this perimeter information, and we were able to solve for one variable, plug it in, and eliminate the w. Now we have area strictly as a function of x. Now we can see pretty easily if I distribute, I'm going to get negative x squared, right? And that's my parabola. There's my quadratic function. So I have my area as a function of x. Right? So I decided to go ahead and use function notation here. I said a of x. Right? That's like my f of x notation. So here's my quadratic function. Area is a function of the dimension of length. So now I just need to find the vertex of this parabola, and there's my maximum value. Now again, the parabola opens downward because the leading term is negative, so I know the vertex will be a maximum in that case. Right? So if I were to do negative b over 2a, right, here's b over 2 times negative 1, right? So I do the negative of b over 2 times negative 1. I'm going to get the x value of 500. Right? And again, remember, the x value is the length. So what I did on the graph here was I pointed out to ourselves that x value is the length. Right? So I have the length as 500 feet. So if I choose a length of 500 feet, then I'm going to get the maximum possible area of 250,000 square feet. Remember, area is square feet, right? So if I choose a length of 500 yards, right, what would the width of the rectangle be? Right? So I already knew down here the width would be the 1,000 minus the x. So if the x is 500, then the width is also 500, and then there's my area, there's the dimensions that produce the max area. All right, now, so in this problem, let me point out to you, it only asked for the dimensions that produce the max area. Right? And so there's the dimensions, 500 by 500. But I also discussed with you, here's the area value. Here's the maximum area. So here's my area parabola. Here's the y value of that parabola. That is the max area. So had this problem asked for what is the maximum area, we would say 250,000 square feet. But in this case, it didn't ask for that. All right, in this next example, let's focus a little bit on technology here. So here's problem about projectile motion. We talked about at the beginning of the first section, 4.3, that the most simple, basic, well-known examples of quadratics are projectile motion problems. So here's an example. The problem says a projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. In physics, is it established that the height h of the projectile above the water is given by this equation? So here's the x squared term, right? So I want to point out to you the ax squared, right? The a is negative 32 over 400 squared. There's my a value. And then plus bx, so the b is 1 and the c is 500. So here's a little visualization, right? It looks like here's a cliff and then here's some water below it, right? So here's the cliff and we're going to shoot the cannonball, if you will, at a 45-degree horizontal, and it's going to land here. So x is the horizontal distance of the projectile from the base of the cliff. So you can see here's the base of the cliff where it touches the water. So x is this horizontal distance that the cannonball travels, right? And y is the distance, the height from the surface of the water. So this is the height from the surface of the water, 1,000 feet from the base of the cliff. Okay. All right, now so letter A says, using your calculator, find the maximum height of the projectile. And before I do that, I just want to point out to you, we could find the maximum height with pencil and paper. We don't need technology for this problem. We know the b value is 1. We know the a value is negative 32 over 400 squared. So we could do the negative of b over 2 times a. We could find that value pretty easily. All right? Let's go ahead and use the technology since that's what they asked for here. So I'll bring out my calculator and let me turn it on. Let me clear out these old equations and I'm going to graph. So I'm going to use parentheses like we talked about before when I do fractions. So for this first fraction, I'm going to put a parenthesis. I'm going to do negative 32 and then my variable x squared. So let me close the numerator and then I'm going to divide by, and I'm going to parenthesize the denominator. I'm going to do 400 squared. So there's that first x squared term, and then I got plus x and then plus 500. Now look, obviously when I graph, I don't see the graph, right? And the reason I don't see the graph is because my window is going from minus 10 to 10 on the x-axis, minus 10 to 10 on the y-axis, right? And that obviously is not what's going to work here, right? So the graph that's given to me within the problem shows me that I should go out, beyond 5,000, let's say to 6,000. So 0 to 6,000 would be a good viewing window. Now, obviously, negative distance doesn't make sense here, right? Because we're shooting a positive distance away from the cliff. Okay. Also, negative y's don't really make sense here either. If we're not considering the cannonball going below the surface of the water, right? So let me go to my window and let me change my x-min to be 0, my x-max to be 6,000 as is implied by that graph, and let's put tick marks every 1,000 as was done on that graph as well. And then let's make our y-min be 0, our y-max be 2,500 again as was done on that graph, and let's do tick marks every 500 units as was done on that graph. Right? So if I hit graph, there's that projectile picture that I see. All right, now again, I could do negative b over 2a and find the vertex, but this problem said use technology. So let's use technology, right? So how would I find that maximum there? So I'm going to do second trace, go to the calc menu, and I'm going to choose number 4, the maximum. And it's going to ask me for left bound, so I'm going to click my arrow. I'm going to move to the left of the maximum and hit enter, and then I'm going to have to enter a right bound. So I'm going to move to the right of the maximum and hit enter. And then I'm just going to hit enter a third time for the guess, excuse me, and it's going to locate the max min of the graph. All right, now, for this particular problem, keep in mind that the x-coordinate is the distance from the cliff, right? So I got 2,500 feet from the cliff. The ball will have traveled here to this point, and then it will be a height of 1,750 feet. So that's my y value that's here as well. Okay, so I went ahead and just kind of plotted and labeled that point. There's that max value, right? So letter A says find the maximum height of the projectile. So that would be the y value here of 1,750. Okay, and then letter B says use your calculator to determine how far from the base of the cliff the projectile strikes the water. Now for a TI calculator, right, so we're finding this x-intercept. For a TI calculator, finding that x-intercept's a little bit trickier. So here's what I'm going to do on my graph. I need to see below the x-intercept on my TI. Right? So I'm going to go to my window and I'm going to open up the y-min to be like negative 1,000. So I want to be able to see below the y-axis, excuse me, below the x-axis. Right? So again, I show you how to do this in Blackboard. The tutorials are there, but let me walk through this real quick. So I'm going to do second trace, go to the calc menu, and this time I'm finding a 0. Right? That's the x-intercept. So it wants a left bound, excuse me. So if you think about left bound for an x-intercept, right, if I move over here to the x-intercept's about right there. So I'm going to click to the left arrow and move to the left of the x-intercept and say there's the left bound. And then it wants a right bound. So this is why I needed to see below the axis. So I'm going to click to the right a couple times to see below and give a right bound. Then it wants a guess, so I'm just going to hit enter, and then there's my x-intercept. So this is an approximation. So if I round to the nearest whole number, I got 5458 to the nearest whole number would be that x-intercept. All right, so I round into the nearest whole number. There's my x-intercept. So how far from the base of the cliff will the projectile strike the water? It'll be 5,458 feet that it strikes from the water. And here's one of the things I love about Desmos is it's so easy to zoom in and out. I can just hit these zoom in and out buttons, right? I can zoom out until I start to see the graph. There's the graph. So I can just kind of scroll. Oh, there's the graph. All right, so really easy to find it. The only thing I love about Desmos, right, is I can click on the graph and it assumes I want to find x-intercepts, y-intercepts, max and min values. So I can very easily find that max value and find that x-intercept as well. Okay, so in summary here, the max height of the projectile was 1,750 feet. That was my y value, and the projectile would strike the water about 58 feet from the base of the cliff. Okay, so the last example we're going to look at here is another problem where they don't give us the equation of the parabola, so we're going to have to build this equation. So let's take a look at this problem real quick. It says the Golden Gate Bridge, a suspension bridge, spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from two huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. Find the height of the cable at a distance of 1,000 feet from the center. So again, they told us that the two towers are 746 foot tall. So to make life easy on ourselves, what we're going to do with this parabola is we're going to put the vertex right at the origin. So we're going to put the origin, here's the y-axis, here's the x-axis. We're going to put the vertex at the origin. It's just going to make it so much easier to find the equation. So if we situate the parabola that way, goodness gracious, excuse me, the towers are 746 feet tall, right? So here's the 746 foot tall tower, right? And since we're told that the roadway is 220 feet above the water, we're going to subtract 220 that we have here, and that's going to leave me left with 526 for this y value. Again, they tell me that the towers are 4,200 feet apart, so we're looking at 4,200 feet total distance. So half of that distance gives me to the origin, and then the other half. So this is going to be negative 2,100 on the x-axis, and then this is going to be positive 2,100 over here as well. So I can plot those 2 points on the parabola. Now that's really all the information we needed. This information about the cables being 3 feet in diameter, we don't really need that here. The 90-foot wide roadway, we don't care about that. That's not what we need, right? That was just kind of extra information. All right, so we just kind of simplified this picture here because it was pretty cluttered, right? Here's my parabola sitting at the origin. Here's the 2 points that we plotted, right? And then the question is asking us what's the height of the cable 1,000 feet from the center of the roadway. So if this is 1,000, what's the y value? So we need to build the equation of this parabola, and this is not really going to be that challenging. So think about, since we have centered this parabola with the origin right at the vertex, this is a really simple equation. This is just the form y equals ax squared. There's no shifting to this parabola in any way, shape, or form. So this is a pretty simple equation, y equals ax squared. And here's 2 points on the parabola. So I could literally plug this x and this y into the equation, and that finds that coefficient for me. So I'm going to do that. Here's the x value, here's the y value, and then I'm just going to divide this to the other side, and there's my a. So I have this a value for my parabola. Here's my equation of the parabolic shape of the wire, the suspension wire for that bridge. Okay? So I'm just going to use that equation then. I'm going to plug in 1,000, right, to find the height, y, when x is 1,000. So if I plug that in, there's my y value, which is going to be about 119.27 feet.